recording. All right. So I want to add a few words about the sum of squares. You know, last time we gave you the sum of squares, and then we gave you the definition. We also gave you the equation that the SST equal to sum of SSR plus SSE. So SS stands for sum of squares, T is for total, R is for regression, E is for error. So not only this equation holds for the numerical values here, but also it holds for the degree of freedom. So what is the degree of freedom for SST, for SSR and SSE? I can put it here. So SST, you have n-1 degree freedom. For SSR, you have 1 degree freedom. For SSE, you have n-2 degree freedom. Then you can see here, the n-1 equal to 1 plus this, okay? The equation still holds if you look at the degree freedom. So when you consider they are as a random variable, not only the values coming from the random variable holds, but also their degree freedom. Now, how come we have n-1 degree freedom for SST? So this is a skill you need to learn for this class. For any random variable, you should be able to figure out what is the degree of freedom. So what is the reason we have n-1 degree freedom for SST? Anyone? How do you figure out the degree of freedom by yourself if it's not given? And for the fact that SSE has n-2 degree freedom, we have already used it, right? When we use the test, we defined a t-test. So basically, for t-test, you have to look for a t random variable that has n-2 degree freedom. So that n-2 comes from here originally. So to figure out the degree freedom is very important here. So how come it is n-1 for SST? If you are unfamiliar with that, maybe just write out the equation. SST is summation I goes from 1 to n data points in the sample, right? Sum of squares. Each one is yi minus y bar squares. So how come it's n-1 degree of freedom? You have n data points. Each one is independently obtained, right? Each observation yi is independently obtained. So that's n free pieces you can move around. However, when you calculate y bar has formula summation yi divided by n. When you calculate y bar, you used 1 degree freedom. In other words, you have 1 constraint. So n free pieces, 1 constraint. That's why you have n-1 degree freedom. Okay? Any questions for this part? No question at all. Okay. Now, SSR, how come it has 1 degree freedom? SSR is summation of yi hat minus y bar squares. I goes from 1 to n. How come this one does not have n-1? The previous one have n-1. The structure looks very similar. How come this one only have 1 degree freedom? Any idea?
Is it because you're using an estimated value in there with the yi hat?
It is, but how come replacing yi by yi hat, you lose so much degree of freedom? What is exactly the reason here?
Because of the potential error with the estimation?
Not quite. So basically, when you look at this formula, this is yi, each yi has beta 0 plus beta 1 xi plus epsilon I. Epsilon I are usually IID normal, right? So you can freely choose the epsilon I value. So each yi is independent of others. So that's n free pieces you can move around. However, when you replace yi by yi hat, when you have yi hat, how do you calculate yi hat? You have beta 0 hat plus beta 1 hat xi. when xi is given, you have two things to decide the value of y hat. That's beta 0 hat and beta 1 hat, right? And each of them coming from a formula that's a function of the data points xi and yi's. So y hat here, there are only two free pieces. Then when you calculate the y bar, you lose one. So 2 minus 1. You don't have n minus 1, you have 2 minus 1, because two pieces decide the value of y hat. Unlike yi, each one you can decide yi freely for each I. For yi hat, when xi is given, you only have beta 0 hat and beta 1 hat, two pieces to move around. Okay, so two free pieces minus one constraint, so you have one degree freedom. All right. Now similarly, of course, once you figure out this two, for this one you can just use n minus 1 to arrive at n minus 2. However, just by looking at SSE alone, you should be able to figure out what's the degree freedom. This is a summation of yi minus y hat squares. Okay, so yi, you have n free pieces. That's n degree freedom. When you calculate y hat, you have two equations. Beta 0 hat equal to blah, blah, blah. Beta 1 hat equal to blah, blah, blah. Each of the beta 0 hat and beta 1 hat is a function of x and y. It didn't increase your degree freedom, but instead you have two constraints to satisfy. So that's why n minus 2. Is that clear for everybody? How do you figure out the degree freedom?
Can you please go through that again, please?
Which one? SSE?
How you got the degree of freedom? Hold on,
it's not very clear. So you want me to go through which one again?
The explanation of the degree of freedom, how you came about that. I was having issue with my computer earlier, so I didn't get that clearly. Do you mind?
It's still very, I still didn't get it. Can you type here? Can you type here? No, okay.
Prof, let's just go ahead, it's fine. I'm gonna figure it out, it's fine, thank you.
Okay, all right. So basically you, for each equation, you look at how many free pieces you bring in the equation. In this case, in the SSE case, the free pieces are the yi. You have n free pieces. Y hat is not a free piece because when you calculate y hat, you use beta 0 hat and beta 1 hat. You basically have an equation beta 0 hat equal to something, beta 1 hat equal to something. Each one of the equation is a constraint you have to satisfy. Before you bring y hat into the formula, you have to satisfy this constraint. And these are the xi and yi's. So n free pieces, two constraints. So you arrive at n minus 2 degree of freedom. Okay, so the general formula for all of that is the number of free pieces you can freely set the value without conflicting or interfering with others. That's the initial gross degree freedom minus the number of constraints you have to satisfy. So in this case, that's 2. Okay, so that's why you get the minus 2. Okay, so this is important because in the future, you probably still need to figure out degree freedom when we have multiple variables, when you have multiple linear regression. Yes, a question?
Professor, could you explain how you got 1 for SSR again?
1 for SSR? Okay, so when you have yi hat, you don't have n free pieces, you only have 2. Assuming you can freely set beta 0 hat and beta 1 hat, that's only 2 free pieces, right?
Yep.
You don't have, y hat does not have n free pieces for I equal to 1 to n because each y is calculated by y hat equal to beta 0 hat plus beta 1 hat xi. Xi is not considered a random variable. That's very important to know, okay? Here, the random variable is yi. So in this case, once xi is given, you have 2 free pieces to move around to decide the value y hat. Yeah, that's 2. 2 minus 1 constraint. When you calculate y bar, you use the summation of yi divided by n. That's a constraint.
Mm-hmm.
So two free things minus 1 constraint, you arrive at 1.
Okay, makes sense. Thank you, Professor.
Yeah. Why? Okay, here's the question. Why y hat has n degree freedom? No. Y hat has 2 degree freedom. So in this case, you consider 2 because you only have 2 free pieces to move around with. Okay, yeah, okay, you got it. All right, so this is a little things I want to bring to your attention. So today we are going to move on to the next section. This is in section 2.7, confidence intervals. Last time in section 2.6, we talked about the testing, how to test a hypothesis. So in confidence interval, we are interested in find what is the range that contains the true parameter. So when you mention the word confidence interval, what follows that is always what is confidence interval of something. This one is always a true parameter. Okay, you talk about the confidence interval of a unknown true parameter. For example, the beta 1 or beta 0 in the population regression line, it's never known, right? But you don't know the exact value, but you can have an interval to tell you that, okay, the true value must be within this range from here to here, and with a certain probability. Let's say I'm 95% confident that the true value, beta 1, is within this range. It doesn't need to be in the center, but it is in this range. So that's the meaning of confidence interval. Okay, so before we have the confidence interval formula, we need to review the distribution, the sampling distribution of beta 0 and beta 1. Remember in the previous lecture, we gave you that beta 1 hat follows normal distribution with mean equal to the true parameter beta 1 with variance equal to sigma square divided by summation of xi minus x bar squares. That's variance. And beta 0 hat follows normal distribution with true parameter beta 0, and variance is the sigma square multiplied by 1 over n plus x bar squares divided by summation of xi minus x bar squares. Okay, so that's the variance. So with this, we can either do testing or do a confidence interval. Either way, we have to follow this distribution here. So this is in case when the true sigma squared is known, you use the true sigma squared. So if sigma squared is unknown, the estimated sigma squared hat, this is defined as SSE divided by n minus 2. So use this if the true sigma square is unknown. Okay? Use estimated variance if the true sigma square is unknown. So most time our interest is to find the slope, the confidence interval for the slope. Less interest is to find the confidence interval for the intercept. But still, the methodology is the same. If I give you the methodology for finding a confidence interval for beta 1, you should be able to follow that. Just copy what I do here to find the confidence interval for beta 0. Okay, so our focus here will always be on the slope. So let's say you have let's say alpha is given, just like here, I'm saying 95% confidence interval. The 95% is 1 minus alpha multiplied by 100%. Okay, so this is the meaning of 95. In this case, alpha equal to 5. Sorry, 0.05%. So alpha usually is given. If somebody asks you to find confidence interval of two parameters, they always express the significance level alpha. Then 100 1 minus alpha % confidence interval for the true population beta 1 is, I give you the formula first, then we talk about how do we arrive at this, how do we derive that. So this is your point estimate. You basically use beta 1 hat as a point estimate, plus and minus t alpha over 2 and minus 2. This expression means the cutoff value for t distribution with n minus 2 degree freedom, the area under the curve at the tail is alpha over 2. Okay, this one multiplied by the standard error of beta 1 hat. Okay, so beta 1 hat is a point estimate. This plus and minus is the half length of the interval. So basically you have a interval, you have lower bound and upper bound. At the center of the interval is your point estimate called beta 1 hat. You are using beta 1 hat to estimate beta 1. So this is the point estimate. So if you do minus, you get the lower bound. If you do plus, you get the upper bound. So it's a point estimate plus minus half length of the interval. Okay, the half length here is given by the t threshold cutoff value multiplied by the standard error of beta 1 hat. Okay, so how do you come up with the standard error of beta 1 hat? Well, you have the variance here. If you don't have the true sigma square, use the sigma hat square. Square root of that is the standard error. So the standard error of beta 1 hat is given by square root of sigma hat square divided by summation xi minus x bar squares. Okay, so that's the formula. How do we arrive at here? How do we derive that? So first of all, you need to understand the meaning of constant interval. So the meaning of constant interval, so basically when I say 95% constant interval of beta 1, that basically means the probability that the true parameter beta 1 is within this interval is 95%. Okay, so basically you are talking about the probability that the true population parameter beta 1 is within this interval is given by this percentage. If alpha is 5%, this will be 95%. Okay, so how do we express that beta 1 is within this interval with 95%? So first of all, you need to understand all the cutoff value. When we are able to find the cutoff value, you first need to go back to a distribution. To find the distribution, then you find the area under the curve, find the tail probability. So we defined, let's say t equal to beta 1 hat, your point estimate, minus the mean of it, divided by standard error of beta 1 hat. This is a t distribution, right? Beta 1 hat follows normal distribution here. A normal random variable minus the mean divided by the standard error of it give you a t distribution. If I'm using the true population parameter sigma squared, you would get the standard deviation of beta 1 hat. Okay, it will be a normal z distribution instead of a t distribution. So right now we are using the sigma squared, sigma hat squared. So this one is a t distribution. So the value t is totally computed from samples, right? It is totally computed from samples. So this one follows t distribution with n-2 degree freedom. Then we can talk, once we have a distribution, we can talk about what is the probability that the t absolute value greater than this threshold t alpha over 2 n-2 degree freedom. What is probability? This should be exactly alpha, right? How do you know? You have a t distribution, center 0. You have alpha over 2 area under the curve, alpha over 2 area under the curve. So the probability for absolute value of t to be greater than this threshold, the threshold is right here. This is t alpha over 2 n minus 2. This would be negative t alpha over 2 n minus 2. It's symmetric around 0. So the probability for the absolute value of a t random variable to be greater than this threshold is exactly alpha over 2 plus alpha over 2 equal to alpha, okay? This is very important to know. So once you know the probability for the absolute value to be greater than, you can easily figure out what's the probability for the t absolute value to be less than that. That should be 1 minus alpha, right? So in that case, the probability for the value of t to be within this is exactly 1 minus alpha. So negative t alpha over 2 n minus 2 degree freedom less than t less than positive t alpha over 2 n minus 2 degree freedom. The probability for t to be between these two is exactly 1 minus alpha. So in other words, the area under the curve for the middle part, the red part, is 1 minus alpha, okay? It's a probability, because when we talk about probability, it's a value between 0 and 1. So we just use 1 minus alpha. It's naturally a value between 0. But once you use the expression, the confidence interval, you usually use a percentage. That's why you need to multiply that. Instead of 0.95, you would say 95% of confidence interval. All right. So we figured that the probability for t to be between these two is 1 minus alpha. So what do we do next? Next is we already defined the t to be this, right? We just need to plug in the formula of t in this, right? So probability, copy down the lower bound, just replace t by our definition. So you have beta 1 hat minus beta 1 divided by standard error of beta 1 hat. That's the definition of t. Less than t alpha over 2 and minus 2. So this and this is equivalent because all I did is just replace t by its definition. It will be still 1 minus alpha, right? And this one, this inequality, actually it's two inequalities, can be changed to something equivalent. So you basically, you want to find the interval for beta 1, you basically just put beta 1 in the middle, then you find the lower bound and upper bound for that. So write that in the form probability of for beta 1 to be greater than something and less than something, okay, equal to 1 minus alpha. So what is the lower bound for beta 1? The lower bound, if you look at this side of the equation, this side of the inequality, you can find that beta 1 is greater than beta 1 hat minus this multiplied by this, right? On the other hand, if you look at this side of the inequality, you'll find that beta 1 is less than beta 1 hat plus this multiplied by this, because there's negative sign, move to the other side, it becomes a plus. So working on the two inequalities, you get the lower bound, which is beta 1 hat minus the threshold multiplied by standard error of beta 1 hat. Okay? The upper bound will be beta 1 hat plus the threshold value multiplied by the standard error of beta 1 hat. So that's how we come up with the formula for the confidence interval. So eventually you get the probability for beta 1 to be between this lower bound and this upper bound is exactly 1 minus alpha, okay? So this gives you the equation, the formula we have here. The formula we have here is beta 1 plus or minus this threshold multiplied by this. Minus is for the lower bound, plus is for the upper bound. Okay, this is how we derive that. So any questions so far? So eventually you say that, let's say that 95% confidence interval for beta 1 is this and this. You can either use this form, you can either use the form of beta 1 hat plus or minus something. You can also say beta 1 is in the range of a lower bound and the upper bound, okay? This is how you express the confidence interval. All right. So this is just to find the confidence interval of a true population parameter. So can you also use confidence interval for hypothesis testing? Earlier, we talked about hypothesis testing by using t-test, right? We use the rejection region. Can you also use the confidence interval to do hypothesis testing?
Yeah.
This should be in your previous slide. 474 or 470, yes. So you basically, you can you can have 3 ways to do hypothesis testing. Let's say you try to do hypothesis testing for the null says the beta 1 equal to a hypothesis value beta 1 not. The alternate says the beta 1 is not equal to the hypothesis value beta 1 not. This 0 here just to indicate that this is the hypothesis value in the null. So you have how many ways to do that? The first way is, of course, use rejection region, right? Use rejection region. So basically, you define the t like so. You have t random variable. If the absolute value of the t calculated from the samples is greater than the cutoff value t alpha over 2n minus 2, you basically reject the null. This is the content in the previous section. Use rejection region to do the hypothesis testing. The second one will be use the confidence interval we talked about today. Use confidence interval. How do you use confidence interval to perform testing? Yeah, so basically, if the confidence interval contains the hypothesis value, you fail to reject it. Okay, if the confidence interval includes the hypothesized value, you fail to reject. If your hypothesis value beta 1 not is not included in the confidence interval, you would reject it. Okay, if the confidence interval does not include the hypothesis value beta 1 not, in that case, rejected null. So in other words, if you have a confidence interval for beta 1, you would say, okay, 95% of chance the true parameter should be within the range. However, the hypothesis value is somewhere outside, either left side or right side. Your hypothesis value is not in the 95% of the confidence interval, let's say. Usually alpha is given as 5%, but sometimes alpha given as 10%. So the value of alpha could be different, but I'm just using 95% as a example here. So you would expect if the null is true, then in this region, from here lower bound to here upper bound, you have 95% chance to include the true population parameter. However, your hypothesis value is not in. That basically means what? That basically means when you assume the null is true, it's a wrong assumption. That's why you should reject it, okay? If the interval does not include the hypothesis value, you should reject it. What else can we do for hypothesis testing? We also have the third method called the p-value approach, right? P-value approach asks you to calculate the probability. So comparing probability instead of comparing the cutoff value. So for this, now this is a two-tailed test. So you basically, the p-value equal to 2 times probability for the probability for a t distribution with the same degree of freedom to be greater than the absolute value of your calculated t, okay? So this is a t random variable with, in our case, it's n minus 2 degree freedom. This is something you look up from the table. This lowercase t is what you calculated from your data, okay? This is from your calculation. So basically, you're looking at what is the chance you can observe this t value. You know the t distribution is n minus 2 degree freedom. In the t distribution with n minus 2 degree freedom, you have a t value calculated by you. Sometimes it's positive, sometimes it's negative. In this case, we compared absolute value. So you calculate, okay, this is my t, calculate from data. What is the chance for me to observe a t distribution to be outside of this? Okay? So 2 times the tail. If this probability is large, then what? If your probability is large, that means if the null is true, it's very likely you are going to observe t at this location. But if your p-value is small, let's say small enough, how small is small enough? If it's smaller than the significant level alpha, you should reject. So basically, if the p-value you calculate by using formula is less than a specified alpha value, you would reject the null. Okay? I see some questions going on here. Let's see what's it. So you are discussing with among yourself, right? Any question for me? Okay. Looks like you have helped each other. So basically, you can have 3 ways to do hypothesis testing. Either use the direct rejection region, calculate t-value like this. So basically, you put your hypothesis value beta 1, 0 to here. If it is greater than the cutoff value, reject. Or use confidence interval. If the confidence interval does not include the hypothesis value, reject. Or you can calculate the p-value. For two-tailed test, p-value equals 2 times probability to observe a value greater than this. If the probability is still too small, less than a specified alpha value, then you reject. Okay? Any questions so far? No question. Okay. So next, let's look at what are the factors that can change your confidence interval. So first of all, do you think the confidence interval should be wider or narrower? Is it the wider the better, or is the narrower the better? For the same alpha value, let's say given alpha value, do you want your confidence interval to be narrower or wider? Which one would you think? Narrower. So you want it to be narrower. So narrower means precision. Wider means, okay, you didn't give me enough information. So I could say, okay, with 100% of confidence, the true population parameter beta 1 is located between negative infinity to positive infinity, which is a correct statement, right? Because any value is between negative infinity to positive infinity. However, you didn't give me any useful information. The confidence interval is too wide to be useful. If you could narrow down that to a small range, that's better, that's helpful, right? So for the confidence interval, narrower means better, means precision, okay? So what decided the width of the confidence interval? The confidence interval width. You know, it's symmetrical around the point estimation, so you basically just need to talk about the half width, right? So it is 2 times of the t alpha over 2 n minus 2 multiplied by standard error of beta 1 hat. That's the width here, So in what case, if something changes, the confidence interval width will change. So let's say if alpha increase, what will happen to the confidence interval? So you double down wider. Okay. Really? You look at the picture I draw here. Alpha over 2 is area under the curve, right? If alpha increase, this interval becomes narrower or wider. If alpha increase, what happens to the confidence interval? First of all, as alpha increase, is your confidence level increase or decrease? Your confidence level is 100 times 1 minus alpha percent. Yes, as alpha increase, remember alpha is at the tail position. Its area under the curve at the tail is alpha over 2. So as alpha increase, your confidence level, do you become more confident or less confident? Increase or decrease? Decrease, okay. As alpha increase, let's for example say alpha equal to 5%, my confidence level is 95% confident. If alpha becomes 10%, the confidence interval, I would say I'm 90% confident, right? So 90% confidence interval. So as alpha increase, your confidence level decrease. Your confidence level decrease. What happens to your confidence interval width? Remember what I just said. I'm 100% confident that true value is between negative infinity to positive infinity. When your confidence level decreases, you are less confident now. Your confidence interval width should decrease, okay? This can also be observed from the t-value, right? So t distribution is here. As the confidence interval is 2 times this, you just look at the half length here. Let's say the standard error here, this one doesn't change because it has nothing to do with alpha. This one has something to do with alpha, right? So the area under the curve here is alpha over 2, okay? As alpha increase, this value would move to this direction, right? In order to give it more area. As alpha increase, this cutoff value will move closer to 0. That basically means this t value will become smaller. Your confidence interval width will decrease, okay? Yeah, make sure we know what is good thing, what is bad thing. Alpha increase is not a good thing. You are less confident. Your confidence, of course, with the same data, your confidence interval width becomes smaller. That basically means you are given smaller interval. It's more precision. As it becomes more precise for the interval, you are less confident. Okay, with the same data, it's a trade-off. On the other hand, if let's say alpha equal to 2.5%. I'm talking about 97.5% of confidence interval. Your confidence interval will become wider if alpha decrease here. And your confidence level increase from 95 to 97.5. So your confidence level increase. It's kind of a pair of a trade-off with the same data. Okay. So secondly, as your sigma hat square decrease, sigma hat is Sigma hat squared is your estimated variance. If your estimated variance decrease, what happened to the confidence interval width? With the same alpha. When I say this one decreased, it means everything else will remain the same. So if your estimated variance becomes smaller, look at the formula for standard error for beta 1 hat. Standard error for beta 1 hat has this in here. So if this one decrease, standard error for beta 1 hat decrease. So that basically means if everything else remains the same, this one decrease, then your confidence interval width will increase or decrease? Decrease, right? If your estimated variance becomes smaller, your confidence interval width decrease. So with the same confidence level, you are more accurate now. You become more precise. So in statistics, having large variance is not a good thing. Having small variance, even though this estimated variance, is a good thing. Okay. So what else will change your standard error for beta 1? So in the formula, you observed hat squared. On the other hand, you also have summation xi minus x bar squared. Okay, if the data is more spread out, like in the regression line here, instead of narrowly focused on one small area, you can make the data more spread out. In that case, xi minus x bar squared will increase. It's at the bottom. So if this thing increases, the standard error for beta 1 hat decrease. So if the data more spread out, then what? If the data spread out, then the standard error for beta 1 decrease, and the confidence interval width will also decrease. So your goal is to have a narrow confidence interval, so it is precise. So you want to have either a smaller variance, or if you cannot change that, if the data is more spread out, your standard error for beta 1 also decrease. Okay. So that is when you have the same number of data points, you want the data to be spread out. Also, if it's possible, you can collect more data points, but it costs money because the sample size is proportional to the cost to collect the data. So as data point n increase, what else? What will happen here? The confidence interval width will decrease. When you have more data, in stat class, usually having more data point is a good thing. Usually, I cannot say 100%, but usually it's a good thing. But it costs money. So as n increase, how come confidence interval width decrease? Well, first of all, the t distribution, you have n minus 2 degree freedom. When n increase, degree freedom also increase, right? T n minus alpha degree freedom here will become narrower. Remember, in the t distribution here, small degree freedom is more flat. Higher degree freedom is narrower, sharper. If you have n equal to infinity, it is pretty much same as the standard normal. So the most sharp one is when n is equal to infinity, okay? So degree of freedom approaching infinity, you will have a very sharp distribution. When it becomes sharp, it becomes narrower, right? Because most data point located around the center is 0. So when you look for the area under the curve alpha over 2, you would look for something here, right? The threshold becomes here. Compared to the flat, when you look at threshold value is here. So basically, the threshold value will be closer to the center. Okay, so the cutoff value, I would write again. So alpha over 2 n minus 2 degree freedom, this cutoff value will be closer to the center, 0. Okay, it will be smaller. If this is smaller, the width will be smaller. And also, as n increase, remember that when you calculate your sigma hat square, you use SIC divided by n minus 2. Even if everything else is the same, increasing n will decrease this. It will decrease this, then you decrease the standard error for beta 1 hat. So basically, as n increase, usually both the threshold value and the standard error for beta 1 will decrease. That's why your confidence interval width will decrease. Okay, so twofold. As n increase, both the cutoff value will be smaller, become closer to 0, and also your standard error for beta 1 hat will be decreasing. So that's why your confidence interval will be decreasing. All right, any question for this part? So out of this, 1, 2, 3 we talked about here has confidence interval decreasing, confidence interval decreasing, confidence interval increasing. So on the other, so basically, if I change the way to ask question, so if I ask which of the following will make the confidence interval width to decrease, and I list 1, 2, 3, 4, you should be able to pick those items, right? Either alpha increase, everything else remain the same, or the estimated variance becomes smaller, or as the data point n becomes larger. All right.
So, Professor, in all these three properties, everything else remains same. We have to assume that, right?
Yes, when we say as one factor change, others remain the same. Yeah.
Sure. Okay, thank you.
If multiple pieces change, and then leading to the conflicting conclusion, you have to use the actual number to calculate to conclude. But once we just pick out one item and assuming all the others remain the same. So this is how it influenced their independent impact on the confidence interval. Okay. All right. So far we have, if alpha increase, is that good? Well, it's not a matter of whether it's good or bad, because the data is the same. In this context here, once the data is given, what you get here is a trade-off between others. If alpha increase, your confidence level decrease, your confidence interval becomes narrower. Your location becomes a smaller, narrower range. However, you are less confident. So it's not a good thing or bad thing. It's a compromise between two factors. The only thing that really improves things is to improve your data. Either you add more data points or make your data points more spread out. So that's the only thing that improves things. Others are the trade-off between what you want. All right. So far we talked about confidence interval. Remember the term confidence interval always is followed by the confidence interval of something. That something is always a true parameter. And the interval have two ends. It has a lower end and upper end. It's a closed interval. So sometimes when we do hypothesis testing, we don't have a two-tailed test. We have one-tailed test. So how does that translate to confidence interval? Because we also use confidence interval to do hypothesis testing, right? So in that case, we no longer use the word or the phrase confidence interval. We use the phrase confidence limit. You either use the lower confidence limit or upper confidence limit, okay? Limit can give you just one value, when the interval always comes with two values, a lower bound and an upper bound, all right? So let's say we want to perform single-sided hypothesis testing or one-tailed test. So let's say one-tailed test. It could be lower tail or could be upper tail. Let's say your null says a hypothesis value is beta 1 equal to beta 1 not. Yeah, alternate says, okay, beta 1 is greater than beta 1 null. So beta 1 not is the one hypothesis in the null hypothesis here. All right. So in order to perform this test, if you use rejection region, what is the format of the language you use to reject? You would say, okay, if the calculated t is greater than something, you would reject, right? If it's a rejection region. So you have a t as defined before. T is the same t we defined before. You calculate point estimate minus the hypothesis value divided by the standard error. So if you use rejection region, you would say, okay, this is t alpha and minus 2. It's one tail test, you use alpha instead of alpha over 2. So if your calculated t is greater than the t alpha cutoff value, you would reject null. Reject null in favor of the alternative, right? Basically, you're accepting that beta 1 really is greater than that. Because under null, if beta 1 equal to the hypothesis value here, you would have very small probability to observe t greater than this cutoff value or threshold value. So when you really observe this value so large, that basically means the hypothesis is not quite accurate. But we are talking about the statistical sense, not in a deterministic sense. So in that case, you would reject null in favor of the alternative, right? So how do we translate into the confidence interval approach? In this case, we don't have a closed interval, we have a open interval with one value given, the other side is open. So basically, we are going to directly use this to develop our confidence limit. So basically, the probability for t to be greater than t alpha minus 2 is equal to exactly alpha. That's precisely the definition of the threshold value, right? For a random variable t to be greater than this cutoff value, the area under the curve is exactly alpha. So with this, we know the probability for t to be less than t alpha minus 2 is 1 minus alpha, right? And then we plug in the definition for t we defined earlier. So probability for beta 1 hat minus the hypothesis value, beta 1 naught, divided by standard error of beta 1 hat. That's the definition for t. Probability for this one to be less than the cutoff value, alpha n minus 2. This is 1 minus alpha, right? And then from here, you're going to have a probability for beta 1 to be larger than. So rewrite this equivalent to this. So probability of beta 1 to be larger or greater than beta 1 hat minus the threshold value multiplied by standard error of beta 1 hat. This will be 1 minus alpha, right? I simply just rewrite this to be the equivalent form. What's inside here? This and this should be equivalent. So you don't have to put the not here, because when you put the not here, this basically means you assume the null is true, right? So let's not worry about this yet. Just put the true population parameter, a symbol you don't know the true value. The probability for this to be less than that translate to probability for beta 1 to be greater than beta 1 hat. Beta 1 hat, I forgot this, beta 1 hat. Okay, minus this 2. Okay, so this is in the form of confidence interval already. However, it is not a closed interval. It is just a lower bound. So this thing here, so probability for beta 1 greater than a lower bound is equal to 1 minus alpha. So where the lower bound equal to this, right? The lower bound just equal to beta 1 hat minus threshold value times standard error of beta 1 hat. That's lower bound. So how do you use this lower bound value to perform the hypothesis testing? So in the interval case, it's easy. We just check if the interval include the hypothesis value. Then you basically fail to reject, right? If it doesn't include, you reject. In this case, you just have a open-ended interval. You only have one bound.
So you're going to check if the value you got is greater than or less than?
So basically, if it is if you plug in the null, it should satisfy this, right? If you plug in the null hypothesis value should be greater than the lower bound. With this is close to 100%. This is a larger value, right? So in that case, you fail to reject. The opposite of that, this one doesn't change. So you are observing the smaller probability, right? So basically, the rationale behind all this hypothesis testing is, if you are observing something that is very unlikely to happen, you would reject. This is the majority of probability. You don't reject if this happens, right? You would reject if it doesn't happen. You would reject if beta 1, the hypothesis value, is less than the lower bound, right? If the hypothesis value beta 1 now is actually less than the lower bound, that probability is alpha. You would reject alpha. You don't reject the 1 minus alpha. Does that make sense to you? Reject the unlikely thing. So how do you reject? If the hypothesis value beta 1 naught is less than the lower bound, you would reject the null. Remember this. If null is true, this is lower bound. The majority of value should be here. You are 95% confident that the true population parameter should be located this way up. However, you are given a value beta 1 naught here, which is outside of this. Consider this is open-sided interval. The other side is infinity. You basically have, you can look at this as a lower bound to infinity. Consider this is a two-end closed interval. In this case, if your hypothesis value is not in here, you reject it, right? Is this clear? Because once the inequality is involved, students always have difficulty. So if your hypothesis value is actually less than the lower bound, you would reject it. Everybody agree? Okay. So it makes sense, right? So this is the right tail. I would put 1 here, then we have 2 to do the left tail. 2, we still have the same null that says beta 1 equal to the hypothesis value beta 1 0. However, the alternate says, okay, the beta 1 needs to be less than the hyperparameter value. Because in real world application, sometimes you are concerned something is too big, sometimes you are concerned with something is too small. So this is left tail, right? So similarly, using rejection region, this is 0, this is negative T alpha and minus 2 degree freedom. The area under the curve is alpha. So using rejection approach, you would reject now if your calculated T value as we defined is actually less than negative T alpha and minus 2 degree freedom, okay? Then we can develop our confidence limit. We call that confidence limit, right? So basically, similarly, using an approach like that, we can write as probability for T to be less than negative T alpha and minus 2 degree freedom equal to alpha, right? That's precisely the definition of cutoff value. Probability for a T distributed random variable to be less than this value is exactly alpha. Then we plug in our definition for T, so probability of beta 1 hat minus the true population parameter beta 1, standard error of beta 1 hat. This T less than negative T alpha. This is exactly alpha. And we want 1 minus alpha, so flip that, so you get probability for this to be greater than negative T alpha and minus 2. When you flip this, it becomes 1 minus alpha, right? And also, you don't need to worry about the equal sign because in continuous distribution, the probability for the random variable to be precisely equal to something is 0. It makes a difference if it's a discrete distribution, but right now T is continuous. So don't worry about the equal sign here. Because I have less than, greater than, I don't have equal here. You don't need to worry about the equal sign. Ignore that is okay. All right, once we have that, can you write out the upper bound? So rewrite that equation, inequality, sorry. So probability for beta 1 to be less than beta 1 hat plus this multiplied by this, right? So beta 1 to be less than beta 1 hat plus T alpha and minus 2 degree freedom multiplied by standard error of beta 1 hat. This probability equal to 1 minus alpha. Okay? So in other words, probability for beta 1 to be less than a upper bound equal to 1 minus alpha. So what is upper bound? Upper bound is this. This is your upper bound. Okay? So basically, you're talking about I have an upper bound here. The true population for beta 1 should be distributed to the left of the upper bound with 1 minus alpha percent, with 1 minus alpha confidence, or with 100 times 1 minus alpha percent is the probability here. Okay. So in this case, how do you perform hypothesis testing? If the null is true, your hypothesis value beta 1 hat should be located below this point, right, to the left, because that's a large probability. The small probability is when you observed beta 1 node here, which is actually larger than the upper bound. Okay, so if your hypothesis value beta 1 node here is actually larger than your upper bound, like this. This is a small probability. Probability for this to happen is only alpha. And you would reject it now. Okay, so this is a hypothesis testing on the other tail. So basically, as you can see, the conclusion is actually the inequality sign here is greater. Your autonym here is smaller. It's always flipped. Your hypothesis testing is to test if beta 1 is less than the hypothesis value, okay? So your conclusion to reject is if your hypothesis value is greater than a upper bound, you would reject it, okay? And so also for the previous one, you want to test if the true beta 1 is greater than a hypothesis value. Your conclusion here is if your hypothesis value is less than the lower bound, you reject it. All right. So that is for using confidence interval approach to perform hypothesis testing. In this case, we don't have a closed-end confidence interval. We just have a one end, called that confidence limit. So any question for this part? I imagine that it would take you some time to flip your head around for the inequality. And this, so basically so far we have done that for the slope. For the intercept, the beta 0, the methodology is exactly the same, except that you just need to replace this. First of all, the standard error for beta 1 hat and beta 0 hat are different. And two, in the T definition here, if it's beta 0 hat, you would use beta 0 hat minus the hypothesis value of beta 0 divided by the standard error of beta 0 hat. The distribution is still T distribution. Everything is the same. It's just the actual distribution for the beta 0 and beta 1 here are different. You need to plug in the right distribution values. All right, any questions so far? Is right to say that the one-tailed tests are less effective than, no. So the reason you have two-tailed tests, sometimes one-tailed tests, is because the interests are different. The hypothesis testing arises from the application, right? Usually it's the alternate hypothesis that contains the research question. The null usually contains the equal sign. The alternate says you either have not equal or greater than something or less than something. Usually your research hypothesis is contained in the alternate here. So it's not a matter of which one is more effective, it's which one is more relevant to your research question, to answer your research question, okay? So basically, right now we don't have an example to ask you to formulate the hypothesis. We directly give you the hypothesis, you just need to perform the testing. But a complete project would include the research question, and you are the one to formulate the hypothesis. Then you would come up with whether you are interested in just the upper tail or lower tail or two tails, okay? It needs to be relevant to the problem you want to solve. It's not a matter of which one is more effective. All right, any question? If no more question, we can ask a poll question and call it for today. All right, polling.